Now consider the eclipsed molecule of ethane. So this eclipsed molecule of ethane have 3 torsional strain pairs. I have already told you about this. So we have to consider the energy values. We have to consider the energy value. By calculating the energy value, we can able to distinguish between the stable and the less stable conformers. How we are going to make a difference between stable and less stable conformer? By calculating the energy value. And those molecules which have less energy are always stable. Those molecules which have less energy are always more stable. So you know the energy values and you have to learn this. You have to learn the energy values, because in exam sometimes energy value is not given, so you have to learn. You have to learn very carefully. So in this eclipsed ethane conformer, this particular bonds have an energy of 1 kcal per mole. It means that we have 1 kcal for this and 1 kcal per mole for this. It means the complete molecule have 3 kcal per mole. That can be converted into 3000 calories per mole. So you have to you should have to able to calculate the values of torsional strain in the organic scaffold very carefully. So what you have to do is you have to first identify the parallel bonds that are cause of strain. So you have to identify those bonds very carefully, because this bond and this bond, because these two bonds are parallel to each other, and due to the parallel bonds are in very close proximity in Newman projection, so that will lead to the formation of torsional strain, and those torsional strain between two CH bond, and those torsional strain between two CH bond have the value that is 1 kcal per mole. Usually we have fixed those values for understanding the conformation chemistry more easier. So for that you have to learn these values. So when two CH and CH bonds are in very close proximity and we have a criteria of torsional strain due to two CH bonds, then the value is 1 kcal per mole. We don't strict to this molecule. In any molecule if you can observe these two bonds, the value is 1 kcal per mole. In any molecule, when you have observed this CH bond, 2 CH bond, and those 2 CH bond leads to the criteria of torsional strain, that particular criteria always have the energy that is 1 kcal per mole. What does this mean? It means that in any conformer, this can be R, this can be R1, this can be R2, and this can be R3. Irrespective of the other substituents, if two hydrogens are present like this, these two hydrogens are present like this in any Newman projection, then those CH-CH bond constitutes the energy that is 1 kcal per mole. So in any molecule, if you are going to observe the two CH bonds, that can leads to the formation of torsional strain in the molecule. So that particular strain value is 1 kcal per mole. Similarly, now we are observing other values. Similarly, if you have this particular, this is staggered conformation of Eclipse, this is staggered conformation of ethane, and this staggered conformation of ethane usually have 0 kcal per mole. Why I am saying this? This staggered conformation of ethane having 0 kcal per mole, because we have 0 pair of torsional strain, and if we have 0 pairs of torsional strain, it means we don't have any energy value. So that's why this is more stable. That's why this particular conformer is more stable, because the energy value is 0, and the lesser the value of energy, the more stability of organic compound. You have to learn this relationship very carefully. Lesser the energy, more the stability. You have to mention this in your notes very carefully. Lesser the energy, more the stability. Lesser the energy, more the stability of organic molecule. Not organic, but in the chemistry this is a fundamental rule. Lesser the energy is, the more the stability of that particular molecule is. So 0 kcal per mole, it means it's a nil energy. So for that, the stability of the staggered is more as compared to Eclipse, and the scientific reason behind that stability I've already explained you. Now consider this conformer in which we have two bonds, CH3 and H. So I have told you that the R1, R2, R3, irrespective of the other group present in any molecule, in any molecule irrespective of the other group, in any molecule, if you are going to observe that particular scenario, that is one bond is CCH3, one bond is CCH3, one bond is CCH3 and other bond is CH bond, then the torsional strain between these bonds are higher than CH bond, and the value of that particular strain will lead to 1.4 kcal per mole. That particular value leads to 1.4 kcal per mole. Why I am saying this? Because 1,4 torsional strain between C and H. 1,4 torsional strain between C and H. I have already told you about the, if 2 CH bond is there, so the value of the torsional strain is around 1 kcal per mole. So why there is 0.4 extra strain? Because of the steric strain. Why? Because CH3 is a bulky group. Because CH3 is the bulky group, and due to the presence of the bulky group, the value will be increased. Due to the presence of the bulky group, the value of this particular molecule increased. So in the conformation chemistry, if you are going to observe the carbon which is connected with a bulky group and the carbon which is connected with the hydrogen, the value will be around 1.4 kcal per mole, because 1 kcal per mole constitutes for the torsional strain between the two CH bonds which are parallel to each other, and 0.4 kcal per mole for those repulsions between two groups, that is CH3 group and CH, because of the bulky nature of the methyl group. The steric strain arises because of the bulky nature of methyl group. So you have to learn the values very carefully. You have to cram this, I must say. You have to learn the values very, very carefully. So for the whole molecule, what's the value? If I am saying you have to calculate the value for whole molecule, that is 1 for this, 1 for this and 1.4 for this. So you have to calculate the value like this. That is, the total value for this molecule is 3.4 kcal per mole. So the total energy of this particular eclipsed conformation is 3.4 kcal per mole. Highly unstable molecule. So if the CH3 and H are present in the eclipsed conformer, then this particular conformer is the least stable. Now come to next conformer. This conformer, when CH3 and H are present away from each other, then we have a 0 kcal per mole, because they are far away from each other, and if they are far away from each other, then we don't have repulsions. Then we don't have repulsions between CH3 and H, and CH torsional strain is also not there. CH torsional strain is also not there, and if CH torsional strain is also not there, then steric strain is also not there, because they are far away from each other. So torsional strain parameter is 0 plus steric strain parameter is 0, because they are far away from each other. So the total energy of this particular molecule is 0 kcal per mole. For this we have 0 kcal as well. Total energy of the molecule is 0 kcal, and this particular conformer is particularly present in this scenario when CH3 and H bonds have 60-degree dihedral angle with each other, then we have a 0 kcal per mole energy. Now consider this particular example. Now we have, this example is for butane. Now I have completed for ethane. Now we are going to learn about the butane. So for butane, what we are going to learn in this parameters for butane in conformation chemistry. So butane have a structure like when 4 carbons are connected in the chain. 4 carbons are connected in the chain, CH3 on this side, CH3 on this side, and 2 hydrogens on this side. 2 hydrogen on this side. So when we are going to form the Newman projection for this, we have to consider one as front and other as back carbon, and these two CH3 as substituents. In the Newman projection, we have to consider these CH3 as substituents. These CH3 as substituents, because we are going to form the Newman projection around these bonds. In organic chemistry, always remember that Newman projection are formed around the single bond. It's a very, very important point that you have to consider. Newman projection always formed around single bond. Newman projection always formed around CC single bond, CH single bond. You have to learn this very carefully. It's a very, very important point that you have to consider, because the Newman projection always formed around single bond. And in butane that we are going to learn in this lecture, we have made the Newman projection. We have made the Newman projection around this particular single bond. This particular single bond. This is our front carbon and this is our back carbon. So in the conformation chemistry of butane. This is front and this is back, and we have taken this bond as a single bond, and we have made the Newman projection on this bond. You can make the Newman projection around this bond as well. You can make the Newman projection around this bond as well. In any conformation, you can, in any skeletal structure, you can form any Newman projection around any single bond. Now you are that much capable of that. So you can form the Newman projection around this bond. You can form the Newman projection around this bond as well. But for our consideration, because the importance around this particular single bond is more, so Newman projection when drawn around this particular single bond is more. So we have considered that. Now consider this particular eclipsed conformation of butane. Eclipsed conformation of butane you have to consider, because I have told you that this CH3, this is CH2, this is CH2, and the particular another is CH3. So this is front carbon, this is back carbon, this is front carbon, this is back carbon, and these CH3 are substituents. And when the two CH3s are present together, then the energy value is 3.4 kcal per mole. And if I say calculate the total energy value, so you have to calculate 3.4, 4.4 and 5.4. So the total energy value for this molecule is 5.4 kcal per mole, because 3.4 for these two CH3 and 1 for this particular bond and 1 for this particular bond. So 1 kcal for this, 1 kcal for this, and 3.4 kcal per mole for this, and the total energy of the complete molecule is 5.4 kcal per mole. It's very important values that you have to consider. This is the eclipsed conformation of butane, and when we are going to form the staggered conformation in this way, this is not staggered, actually this is gauche conformation. This is not staggered, this is gauche conformation of butane. In butane we have 4 conformers: eclipsed, staggered, NT and gauche. I am going to explain each and every conformer in this particular lecture. So just for now, for the values parameter, you have to consider the eclipse as well as the gauche conformation. So when we have two CH3 and we have rotated around nearly 60 degrees, then we are going to get the gauche conformation of butane, and in that particular conformation one CH3 is present on this side and one CH2 on this side. So these two hydrogen have some sort of interactions, that is some repulsions are there, and that the value of repulsion is 0.9 kcal per mole. That is also known as the butane gauche interaction. It's very important for organic chemistry. That is known as the butane gauche interactions. So that is known as the butane gauche interaction. So the CH3 when are present away from 60 degree, or I can say when the two CH3 molecules are at 60 degree dihedral angle, then we have a butane gauche interaction that is usually of 0.9 kcal per mole. So because of these repulsion between two hydrogens, because they are very close proximity, because these two hydrogens are present in very close proximity, that's where the interactions usually arises, and the value is around 0.9 kcal per mole. But when these CH3 enter to each other, then the value is 0 kcal per mole, because this CH3 having this H and this H are away from every other hydrogen that is present in the molecule. This H and this H. When these two CH3 are opposite to each other, then that is known as the NT form. That particular conformer have 0 kcal per mole, because we don't have any repulsion due to torsional strain, due to gauge interactions, or due to repulsions between the hydrogens. So this is the NT form, it's stable. Now observe this very carefully.